Hello and welcome to our Mathematics 2 course. This semester we're going to carry on talking about calculus. Today I'm going to start by giving some information about this course, and then we're going to cover 3 sections. I'm expecting to give approximately 12 courses to you. They'll be on Friday afternoons between 1 o'clock and 3:30. And my plan is I'm going to break this into 2 lectures. And then after the lectures, I'm going to be available to answer your questions. Second lecture will start at 2 o'clock. And between the lectures, we'll have perhaps a 15-minute break, but we'll see how it goes. This course is based on the book Thomas's Calculus, which is the same book that was used in Mathematics 1. This is a required purchase. You need to have a copy of this book, including an access code to be able to do the homework for this course. I'm assuming that most, if not all of you, already have this book from Calculus 1. You can reuse your access code for this course as well. If you have any problems with your access code, then you need to contact Pearson directly, and they will help you out. This semester, we're going to cover 8 chapters of Thomas's Calculus. Chapters 8, 11, 13, 14, and 9, in that order. We'll start by continuing talking about integration. We'll look at some more advanced techniques of integration. We'll start thinking in 3 dimensions. We'll talk about vectors and geometry of space. We'll move on to talking about functions of more than one variable and partial derivatives of them, and then multiple integrals of them. We can think of chapters 11, 13, and 14 as multivariable calculus. And then finally, at the end of the course, we'll change to talking about something quite different that's perhaps not counted as calculus. We'll talk about infinite sequences and series. For the first 3 chapters, I'm going to spend 2 weeks talking about each of them, and then for chapters 14 and 9, I will spend 3 weeks talking about them. We're going to examine this course using both exams and homework. The homework is going to be using Pearson's MyLab website. This is why you need to have a copy of the textbook, which includes an access code. I'm going to give you 12 pieces of homework. So there'll be one based on each lecture. Just in case some students register late or somebody misses a week due to illness or technical problems, I'm going to set the deadline for all of the homework to 1 day before the final exam. So if you really wanted to, you could wait until January before doing the homework. But I think that that would be a mistake. I think most people learn mathematics by doing mathematics. For most people, the best plan would be to try to do 1 piece of homework each week. But I'm being flexible. I leave this for you to choose. If you want to follow my advice and do homework each week, up to you. If you want to wait until January and do it all in one together, again, up to you, or some combination thereof. There will be 2 midterm exams. These will be classroom exams. And then at the end of term, there will be a final exam. And again, I'm expecting that to be a classroom exam unless something changes. Now, if this was a classroom course, you would have 5 hours of lectures per week. And the general rule of thumb is that for each hour of lecture, you're expected to study another 1 to 2 hours outside of class. So that means somewhere between 10 and 15 hours per week. For an online course, you're still expected to study somewhere between 10 and 15 hours each week. Because we only have 2.5 hours timetabled, that means you should be studying by yourself somewhere between 7.5 and 12.5 hours. So what could that include? There's the homework you should be doing on MyLab. I recommend you try to do that every week. Perhaps Friday afternoon after we've finished, you might like to log on to MyLab and do that week's homework to get it out of the way. Recordings of these lectures will be available on both OLearn and YouTube for you to rewatch. I'm making all of the lecture slides available for you. They're not all finished yet. The last few I haven't written yet, but the first 9 or 10 slides are finished. You should be spending time reading the textbook, and you should be spending time solving the exercises in the textbook. There's many exercises in the textbook, many more than I'm asking on the homework. I suggest you open your problem pages in the homework and try to solve as many as you can each week. There's a discussion board in OLearn which you can use to ask questions to me or to discuss with other students. Feel free to help each other with the homework problems and the exercises in the textbook. There's a difference between giving help to someone and telling them the answer. Try to give help to another student without just giving the answer to them. Perhaps you want to read other books, or perhaps you want to watch online videos by other teachers. Before I begin, one more thing to say. I have a slide number at the bottom left corner. This will give you an idea as to how far I am through a lecture. And if you've got your book in front of you and you want to follow along, I have the section title and section number at the top. So let's begin this course. First section that we're going to cover is section 8.1, which is using basic integration formulae. Most of the ideas in this section should be familiar to you. You can think of this section as a revision of some of the ideas from Mathematics 1. Let's start with a table of basic integration formulae from Thomas's calculus. You should be familiar with all of these. I hope you've seen all of these before. Integral of x to the power n, integral of e to the power x, integral of the trigonometric functions, etc., etc. We know these. The hyperbolic functions, sine and cosh. We know how to integrate these. And you will have also seen derivatives of the inverse trigonometric or inverse hyperbolic functions. We're going to be using some of these formulae in this section. First of all, calculate the integral from 3 to 5 of 2x minus 3 divided by the square root of x squared minus 3x plus 1. For an integral like this, we want to use a substitution. And for this one, I'm going to use the substitution u is equal to x squared minus 3x plus 1. Then we need to change dx into du, and we need to change the limits of integration. In this case, du is 2x minus 3 dx. If x is 3, that implies that u must be 1. If x is equal to 5, the upper limit of integration, that implies that u must be equal to 11. Put all of these substitutions in. Our integral changes into the easier integral from 1 to 11, u to the power minus a half du. And you know how to calculate this, so I'll skip forward to the next example. Next one. Find the integral of dx over the square root of 8x minus x squared. And I've put the formula that I want to use at the top in the yellow box. I want to use the formula that the integral of dx over the square root of a squared minus x squared is the inverse sine of u over a. That should be x over a. Typo just here. Plus c. We can't use that directly because we don't have a number minus x squared. We have 8x minus x squared. We need to rearrange our integrand a little bit first. What we need to do is we need to complete the square of x squared minus 8x. And the way that we do this is we add on a number and we subtract a number. I'm going to do plus 16 and then minus 16. Why is it plus 16? Because x squared minus 8x plus 16 is the same as x minus 4 squared. The rule here is we take out minus 8, divide it by 2, and then square it to get the number that we want. So we're trying to find the integral of dx over the square root of 16 minus x minus 4 squared. Now we can do a substitution. We can replace x minus 4 by u. And of course, then du is the same as dx. And this is an integral that now we know how to solve. Using the formula at the top, this is the same as inverse sine of u over 4 plus c. Let's move on to the next example. Find cos x sine 2x plus sine x cos 2x dx. This is straightforward because the integrand is the same as sine of x plus 2x, or sine of 3x. And we know how to do this. Let's move on. Find the integral from 0 to pi over 4 dx over 1 minus sine x. Now, there's a trick if we have 1 over a number minus a number. And the trick is that we multiply it by a plus b divided by a plus b. And then what happens is that we get a plus b divided by a squared minus b squared. And sometimes easier to deal with this. Sometimes a plus b divided by a squared minus b squared is easier to integrate than the function that we start with. So that's what we're going to do here. We have 1 over 1 minus sine x. That's our 1 over a minus b. And we're going to multiply it by a plus b divided by a plus b. And it's easier because on the bottom we get 1 minus sine squared, which is, of course, is the same as cos squared. And then you know how to finish this example, so I'm just going to skip to the next one. Find 3x squared minus 7x divided by 3x plus 2. This is a function where we have a higher power on the top than we have on the bottom. We need to rearrange this. Remember what you did when you looked at oblique asymptotes in Mathematics 1. We can perform long division, however you were taught, and we can write our integrand as x minus 3 plus 6 over 3x plus 2. And then it becomes easier to integrate. Integrating x, that's easy. Integrating 3, again, that's easy. Integrating a number divided by a number x plus a number, again, it's easy, just using substitution. We can find this as 2 natural logarithm of the absolute value of 3x plus 2. Find the integral of 3x plus 2 divided by the square root of 1 minus x squared. Again, there's a mistake here. There should be x just here. Now, first note, we can split this up into 2 integrals. 3 times the integral of x divided by the square root of 1 minus x squared, plus 2 times the integral of 1 over square root of 1 minus x squared. And the green one is easy. For the green one, we just use the formula at the top. Green one is just inverse sine of x. What about the orange integral? What can we do here? For the orange integral, we're going to use a substitution. And we're going to use the substitution, u is equal to 1 minus x squared. Then du, which is du dx dx, is minus 2x dx. Dividing by minus 2, that's the same as saying that minus a half du is the same as x dx, which is what we have up here. So when we do the substitution, our integral changes into the easier integral. Integral of minus a half divided by the square root of u. And this one, you know how to integrate, so I won't talk about the details. Putting everything together, we can write down the answer to this problem. Next example. Find the integral of dx divided by 1 plus root x cubed. I want to do a substitution, but what substitution should I do? My first guess would be to replace the square root of x by u. But this is not going to work. If we do this, then we get du is 1 over 2 square root of x dx, and then we have an extra square root of x term, which adds complication. So I don't want to do this. Let's try again. For my second guess, I'm going to try u is 1 plus the square root of x. Then again, du is 1 over 2 square root of x dx, or dx is 2, u minus 1 du. And when we substitute this in, we get something nice and easy. I will leave this problem to you to finish. I'm sure you know how to solve this at this point. Calculate the integral from minus pi over 2 to pi over 2, x cubed cos x dx. This one's actually easy. This integrand is an odd function. What do we remember from Mathematics 1 when we integrate an odd function between minus a and a? we always get 0. I can show you the graph of this function. We have a positive number and a negative number. Add these together and we get 0. Now, hopefully, that section, which I went through very, very quickly, is revision for you. Hopefully, you understood all of that, because hopefully nothing there was particularly new for you. The second topic that I want to talk about today is integration by parts. How could I calculate the integral of x cos x dx? Or how could I calculate the integral of x squared e to the power x dx? Both of these are integral of a function multiplied by a function. We have a rule for integrating things like this. We have a rule which is called integration by parts. If we have two functions, if the first function we call u of x and the second function we call v prime of x, then this integral is equal to two things. It's equal to uv minus another integral. And when we get to the second integral, we differentiate the first function. U we replace by u prime, and we integrate the second function. We integrate v prime to get v. And sometimes we can use this to turn a difficult integral into an easier integral, as I will show you in the next examples. So I've written the integration by parts formula at the top. We're going to be using that in the next few examples. Find the integral of x cos x dx. We have two functions here. We have the function x and we have the function cos x. But which is going to be u and which is going to be v prime? Remember, we want to make this integral easier. We want to simplify it somehow. One of these two functions we're going to differentiate, one of them we're going to integrate. Let's look first at x. Does this get easier if we differentiate it, or does it get easier if we integrate it? The answer is x gets easier when we differentiate it, because the derivative of x is just 1. So I'm going to choose u is equal to x and v prime is equal to cos x. The orange function we need to differentiate. U prime is 1. The green function we need to integrate, or to say another way, we need to find an antiderivative of the green function. An antiderivative of cos x is sin x. Then we fill these into our formula. First, we want to have uv. So first we want to have x sin x, and then minus the integral of u prime v. That's these bottom two. So we're going to have minus 1 sin x. And integral of sin x is straightforward. We know how to do this. The answer to this problem is x sin x plus cos x plus c. Let's do another one. Find the integral of the natural logarithm of x. Now, what we're going to be thinking about is the integral of the natural logarithm of x multiplied by 1. We know how to differentiate the natural logarithm of x, so this is going to be our orange function, and then 1 will be the green function. So we're going to write u is ln x and v prime is equal to 1. We need to differentiate ln x to get 1 over x, and we need an antiderivative of 1. We'll take v is equal to x. Now we can put these into the formula. That's integral of ln x multiplied by 1 dx is uv, or ln x multiplied by x, minus the integral of 1 over x, or minus the integral of u prime v. And of course, 1 over x multiplied by x is just 1, which is an easy integral to do. So the answer to this problem is x ln x minus x plus c. What if what is higher than 1? I don't understand your question. The 7 is not a problem because we can always just take the number 7 outside the integral. We know how to integrate 1 over x because the integral of 1 over x is just ln x. Let me move on to the next example. Sometimes we need to use integration by parts more than once to calculate an integral. For example, find the integral of x squared e to the power x dx. I'm going to let u be x squared, and I'm going to let v prime be e to the power x. Then this is equal to uv, which in this case is x squared e to the power x, and then minus u prime v. So minus 2x e to the power x. This 2 really should be in orange. But what are we going to do with the integral of x e to the power x? The answer is we're going to use integration by parts again. Now we'll let x be the u function u, and e to the power x again will be the v prime function. Then we get uv, or x e to the power x, and then minus u prime v, or 1 e to the power x, which we know how to integrate. Put everything all together and we get our solution. I should say these are different constants here. So perhaps this one I should call C1 and this one I can call C, because there's a factor of minus 2 in there. We could use the same technique to calculate the integral of x to the power n e to the power x dx. And this time we would have to use integration by parts n times. Each time we use integration by parts, the power of x will decrease by 1 until eventually it will turn into just 1, and we can calculate the integral directly. There's another way to write the integration by parts formula. I've been using the formula at the top. I've been writing integral of uv prime dx is uv minus u prime v dx. But of course, v prime dx is just the same as dv. And u prime dx together is just the same as du. So if we wanted to, we could write the integration by parts formula as the integral of u dv is equal to uv minus the integral of v du. And it's completely up to you which one you want to use. Which one of these do you prefer? I'm going to show you some examples from the textbook now. You will notice that I have some fast examples and I have some slow examples. On the slow examples, I try to explain everything. This is an example of a fast example. I'm just going to pick out the key points and then I'm going to skip to the next one. When you have time later this afternoon or whenever, you can reread this example in your textbook and you can check all of the details there. What are the key parts here? We want to calculate the integral of e to the power x cos x. So we need to decide which is the u and which is the v. This time we're going to use u to be dx and cos x dx we're going to call dv. Then using the integration by parts formula, that's the same as uv. U stays the same. To get v, we integrate cos. And then minus v du. So v we integrate and u we differentiate. Derivative of e to the power x is just e to the power x. Integral of cos is sine. And this is another example of one where we have to do integration by parts a second time. Do the same technique on the integral of e to the power x sine x dx. And we get this term which I've just underlined, minus e to the power x cos x minus the integral of minus cos x e to the power x dx. And we end up with another then we have another integral of e to the power x cos x dx. Now you might think, well, we've just got back to where we started. But because there's a minus sign here, we can take this over to the left side and then we would have 2 times the integral that we want is equal to a function that we know. So we would end up with 2 times the integral we want is e to the power x sine x plus e to the power cos x plus a constant. Dividing by 2 and we get the answer that we want. Another example. Obtain a formula that expresses the integral of cos to the power nx dx in terms of an integral of a lower power of cos x. We want to use integration by parts. We're going to think of the integrand instead of just cos to the power n. We're going to think of this as cos to the power n minus 1x multiplied by cos x. The first one we're going to call u, and the second cos x, the final cos x, will be our v. Or to say it another way, dv will be cos x dx. Then when we do our integration by parts, we obtain the formula which is in the box I've just tried to draw. Let me make that a little bit neater. After we do integration by parts, we end up with this formula which is in the red box. There's a sine squared here. We know what to do if we have a sine squared. We can replace this by 1 minus cos squared. So we have a function, that's easy. We have an integral of cos to the power n minus 2, and we have another integral of cos to the power n. This final one we can take over to the left-hand side. Just as we did before, if we add n minus 1 multiplied by this integral to both sides, we end up with n multiplied by this integral on the left. So we get n multiplied by the integral of cos to the power n is a function plus an integral of a smaller power of cos. And that's what we asked for. Dividing by n, and we get the answer to this problem. So for example, if I wanted to calculate cos cubed, we could use this idea to write this as a function plus an integral of cos to the power 1. Let's move on. You can read the details about that in your book later. I've been talking about indefinite integrals, how to use integration by parts for indefinite integrals. But what about if we had a definite integral? How could I calculate the integral from a to b of u v prime dx? The answer is the idea is the same, but we just need to evaluate everything at a and b. Instead of the first term just being u and v, we need it to be square brackets u, b square brackets calculated at a and b. And then the second integral, of course, is just the integral from a to b. I put this new formula at the top. We're going to do an example using this. Calculate the area of the region bounded by the curve y is equal to x e to the power minus x, and the x-axis from x is equal to 0 to x is equal to 4. So in other words, we want to calculate this area. We're going to be doing the integral from 0 to 4 of x e to the power minus x. We need to use integration by parts. We need to choose a u and we need to choose a v prime. And for this example, I choose u is equal to x, and I choose v prime is equal to e to the power minus x. Then, of course, we have that u prime is 1 and v is minus e to the power minus x. Put these into the integration by parts formula. I get minus x e to the power minus x, calculated at 0 and 4, minus the integral from 0 to 4 of 1 multiplied by minus e to the power minus x. And then it's straightforward. I'll leave it for you to check that the answer to this problem is 1 minus 5 e to the power minus 4. Let's move on to the next example. Find the integral from 0 to 1, inverse sine of x dx. Now, integrating inverse sine of x is difficult, but we know how to differentiate it. Remember that the derivative of inverse sine of x is 1 over the square root of 1 minus x squared. We're going to use this, so I'm going to use the same trick that I used before. I'm going to suppose that the integrand is inverse sine of x multiplied by 1. And then this way, instead of having to integrate inverse sine, I'm just going to be differentiating inverse sine. Here we have that u prime is 1 over the square root of 1 minus x squared and v equal to x. I want to put all of this into the integration by parts formula. First, I have uv calculated at 0 and 1, and then minus the integral from 0 to 1 of u prime v. And the second integral is easy to calculate it. We could just use a substitution if we wanted to. I will leave the rest of this calculation for you to check. When you rewatch these videos or when you read the textbook, please check the details and check that the answer to this problem is pi over 2 minus 1. And that is the end of the first half of today's lesson. I'm going to take a break now. Please relax until 2 o'clock. At 2 o'clock, I'll be back here and I will continue. Let's continue our lesson. We have one more topic to talk about today, the topic of trigonometric integrals. And this will take me another 20 or 30 minutes to talk about. Let's start by talking about some trigonometric identities, which should be familiar to you. What is your question? The current plan is that the exams will be face-to-face. So if nothing changes, you'll have a face-to-face exam in the 8th week of term. If anything changes, then I'll tell you otherwise. Let's go through these identities quickly. Cos squared plus sine squared. This is one I think everybody knows. If we divide by cos squared or by sine squared, we get the next two. Cos A plus B and sine A plus B. Again, you should know these from high school. Replacing A and B by theta, we get the next two. To get the final two, we're going to use the two which are currently in red. Cos squared plus sine squared is equal to 1, and cos 2 theta is cos squared minus sine squared. Combine these two together and we get the last two. We can use these to calculate some integrals. For example, how can we find the integral of sine to the power mx cos to the power nx dx if m and n are non-negative integers. We need to look at 3 different cases. We need to think what happens if m is an odd number. What do we do if m is an even number and n is an odd number? Or what do we do if both m and n are even numbers? Let's look at case 1 first. Let's suppose that m is an odd number. Then we can use this trick. If m is an odd number, then we can write it as 2k plus 1 for some integer k. And then we're going to split sine to the power 2k plus 1 up into sine squared to the power k, and then we'll have one more sine. Because, of course, cos squared plus sine squared is equal to 1. Sine squared we can replace by 1 minus cos squared. And then we're going to do a substitution. We're going to do the substitution u is equal to cos x. And then we'll have 1 minus u squared, just here, all to the power k. And because du will be minus sine x dx, the final sign will disappear. And we'll get something easier. Let's look at case 2. Case 2 is almost the same. If n is an odd number, we're going to write n is 2k plus 1. So we're going to think of cos to the power n as cos squared, all to the power k, multiplied by cos. Replace cos squared by 1 minus sine squared, and then we're going to do the substitution u is equal to sine x. And again, this means the final cos x will disappear because du will be cos x dx. In the final case, if they're both even numbers, we're going to use the formulae for sine squared x and cos squared x. And we'll use these to change our integral into an easier integral. So in all cases, we're going to be using the trigonometric identities and then some substitutions. For example, find sine cubed x cos squared x dx. We're going to be using this 3. 3 is our odd number. This is the one we want. Instead of thinking about sine cubed, we're going to think about sine squared. And then another sine x. The first sine squared we replace by 1 minus cos squared. And instead of sine x dx, this is going to be minus du. So the final sine x is going to disappear. And then we get something easy. We just have the integral of u to the power 4 minus u to the power 2. And we know how to do this. So I can move quickly on to the next example. Find cos to the power 5x. Same trick. We have a 5 here. We're going to think of this as 4 plus 1. So we think that we have cos to the power 4x and then another cos x dx. The cos to the power 4 we write as 1 minus sine squared, all squared. And the final cos x will disappear when we do the substitution. We're going to end up with the integral of 1 minus u squared, all squared, du. And you know how to calculate this integral. Find sine squared x, cos to the power 4x. This time we've got two even numbers. So this is case 3. We use the formulae for sine squared and for cos squared. Sine squared x is the same as 1 minus cos 2x over 2, and cos to the power 4x, or cos squared x and then squared again, is the same as 1 plus cos 2x over 2, all squared. And then it becomes much easier. You know how to do the integral of 1. You know how to do the integral of cos 2x. You know how to do the integral of cos squared. But what do we do about cos cubed? Cos squared is easy. We'll just use the formula again to write this as a half 1 plus cos 4x. Let me move on very, very quickly. For the cos cubed term, we're going to use the same trick that we just did. 3 we're going to think of as 2 plus 1. Cos squared is the same as 1 minus sine squared. And then the extra cos, the plus 1, will disappear when we do the substitution. So this just is the integral of 1 minus u squared du, which is then very easy to do. Put everything together, and I'll leave this for you to check when you read this in your book or you rewatch the lecture. You can check that the answer to this problem is given here at the bottom. Find the integral from 0 to pi over 4, square root of 1 plus cos 4x dx. The first thing is we need to get rid of the square root. To get rid of the square root, we're going to use the formula for cos squared, which if we rearrange it, it says 1 plus cos 4x is the same as 2 multiplied by cos squared 2x. So when we put this in, our integrand becomes square root of 2, square root of cos squared 2x. Square root of a square is the same as absolute value. But for this integral, we don't need to worry about that. If we're between 0 and pi over 4, cos 2x is always a positive number. So we can just forget about these these absolute value signs, and our integrand is just cos 2x, which we know how to do. So let's skip on to the next example. Find the integral of tan to the power 4x dx. I've written two formulae at the top. Tan to the power 4 is the same as tan squared, tan squared. Tan squared is the same as sec squared minus 1. So we end up with integral of tan squared sec squared minus the integral of tan squared. And then again, for the second one, tan squared is the same as sec squared minus 1. Integral of sec squared is easy. We know how to do this because an antiderivative of sec squared is tan. Integral of 1, again, this is easy. So we're left with just the first one, the integral of tan squared sec squared. For this one, we use integration by parts. We'll use the substitution u is equal to tan x, and then du is sec squared x dx. And so this becomes much easier. The first one is just the integral of u squared. Let me move on to the next example. Find the integral of sec cubed x dx. This time we're going to use integration by parts. The 3 I'm going to think of as 1 plus 2. I'm going to think that we have sec x multiplied by sec squared x. I'm going to let u be sec x, and I'm going to let v be sec squared x. Then we know that v is tan x because the derivative of tan x is sec squared. And we know that the integral of sec is sec x tan x. So the derivative of sec x is sec x tan x. And that simplifies our calculation. Put all of these into the integration by parts formula. We get sec x tan x plus the integral of sec x minus the integral of sec cubed x. Take the final integral over to the left to get a 2. We are left with integral of sec cubed x is a half of sec x tan x plus a half of the integral of sec x, which we know. So we know how to do this. Find the integral of tan to the power of 4x sec to the power of 4x dx. Using the left inequality, I can replace one of the sec squareds by 1 plus tan squared. And the second sec squared, I'm going to leave where it is. The second one is going to disappear when we do the substitution. So we end up with tan to the power of 4 plus tan to the power of 6 sec squared x dx. We'll do the substitution u is equal to tan x, and sec squared x dx will be then replaced by just du. We'll end up with an easy integral to calculate. Let's move on. The final idea for today's lesson is, how could we calculate integrals like these? And suppose you're asked to calculate the integral of sine mx, sine nx, or sine mx cos nx, or cos mx cos nx, where m and n could be any numbers. It's possible to use integration by parts 2 times to calculate all of these, but there's actually an easier way. And the easy way is based on the identity at the top. Cos A plus B is cos A cos B minus sine A sine B. I want to use that for cos mx minus nx minus cos mx plus nx. Using the formula at the top, that's the same as cos mx cos nx plus sine mx sine nx minus cos mx cos nx plus sine mx sine nx. And you'll note that we have plus cos m cos n minus cos m cos n. These are going to cancel out, and we'll be left with two sine terms. We'll be left with 2 sine mx sine nx. Divide by 2. The formula that we want is sine mx sine nx is a half cos m minus nx minus cos m plus nx. Similarly, we have formulae for sine cos and cos cos. And I'll leave these for you to check. All comes from the formulae for sine A plus B and cos A plus B. So, for example, find the integral of sine 3x cos 5x dx. We have the formula at the top. Here, m is 3 and n is 5. So we're going to have 3 minus 5, and we're going to have 3 plus 5. We're going to be doing sine of minus 2x and sine of 8x. Here we are. And that's straightforward. I can skip on to the next example. Find the integral of cos 3x cos 2x. Again, I've put a formula that we want at the top. M is 3 and n is 2. So we have 3 minus 2, and we have 3 plus 2. We're going to be doing cos x, cos 1x, and we're going to be doing cos 5x. Etc., etc. You could finish this example if you wanted to. And that is the end of this week's lesson. The first lesson, a shorter than average lesson. Some weeks we'll have longer lessons, some weeks we'll have shorter lessons. I'm now ready to answer your questions if you have any. As soon as I get to this final orange slide, the lecture is finished, and you're welcome to leave if you don't have any questions. Yes, the textbook is the same book that you use for Mathematics 1. if you look in the course content section, I've given the syllabus and I've told you exactly which sections of the book we're going to be covering and in which order. Let me see if I can share that. Oh, I did something wrong there. Here we go. Here's the syllabus. This is the sections that you should be reading each week.